Okay, so unlike my algebra talk last week, this isn't going to be a comprehensive survey. This will just be kind of a light introduction. I think that does it quite well. I just want to give some intuition for what topology is all about to kind of help with the algebraic geometry lectures to come. I mean, they will be self-contained. The professor will define what the topology is there as well, but perhaps kind of in a vacuum. So just some intuition I want to give here. And so to do that, something already kind of mentioned last week when talking about algebra, the kind of notion of doing things locally. And that's really one way of viewing what topology is about. It's about the notion of looking at things locally. And it's a very useful notion in many settings, such as an analysis. So you're taking a derivative, you look at the point locally, you take the local best uh, plane or line of fit to take the derivative. So you really looking at things locally. So just as an example of something happening locally, so let's look at these two functions. We have the absolute value function, the function which squares a number, which are both real valued functions in the set of the real numbers. And here's some graphs. On the left, we have just these two functions, but then I've also scaled the absolute value function down a bit. And something to notice is no matter how much you scale it down, as long as you scale it down by a positive factor, uh, the absolute value function is always near the origin, near zero, larger than the squaring function. So in a sense, locally around zero, you have that squaring a number will always be less than taking its absolute value and scaling it by some positive factor. So this is something captured in general for different functions at other points, also sometimes at infinity, by the so-called Landau notation, which is not something I will get into, but which is, for example, one application of the concepts that will develop of topology. But this just kind of illustrates often phenomena one cares about, they happen locally somewhere, locally at a point. And really one would wish to capture that in some sort of formal definition. And this is what one can do when one introduces later the notion of a topology, topological space, and many other related notions. But for now, let's just look at this example kind of more closely and try to abstract it away. So first, let's notice we can reformulate it just kind of formally as the following. So for every positive lambda, which will be scaling our um, absolute value function by, there is some epsilon greater than zero, some small number possibly, such that if we scale the absolute value function, it's going to be no less than the squaring function if we are evaluating at a point which is epsilon close to zero. So what we do is we interpret the fact that we're locally at zero by saying that we're looking at values of functions at points which are epsilon close to zero for some epsilon. It's kind of in this interval around zero. This is how we can interpret locality. Locality means in some interval, and we'll get to that in greater generality in a moment, but for now, let's kind of first generalize what we're looking at, because here we're looking at this very specific thing, the fact that lambda f of x is greater than or equal to g of x. We can replace it by any property, so let's just kind of give a silly definition of a property, which isn't necessarily wrong, but it's, I mean, a property is a very abstract and vague notion, so there are many possible definitions, but this is one way of thinking about properties. If you have some set, we can say that the property of its elements is just a function which decides for every element of the set whether the property holds or not. So the map just associate true and false. And I mean, strictly speaking, true and false could be anything. You could take the natural numbers 1 and 0 or anything else. We just have to have two values, kind of the Boolean, so to say, which is just some set true and false. And so we can think of a property like this, and above our property would be, say, that x maps to true if lambda f of x is greater than or equal to g of x, and to false otherwise. And generally, we can get this notion of property. So now we can talk about what it means to be true locally, just generalize it as above. So if you have some property, and let's stick to the case of Rn for now, and later we'll generalize, that's kind of the whole point, but let's just look at Rn, so Euclidean space, the set of all ordered n-tuples of real numbers. And let's say you have some point P in Rn and also some property capital P, which takes a point in Rn and decides whether it holds here or doesn't. So then we say that this property holds locally at P, or around P, if there's some distance epsilon, some positive number, such that any point which is epsilon close to P in Euclidean space, so you can interpret epsilon close in terms of this Euclidean distance, which is kind of what you get if you apply the Pythagorean theorem. It's just this quantity, which is the square root of the sum of the squares of the distances between the coordinates. I mean, it's really just kind of the intuitive distance if you identify real life with R3 and measure distance with a ruler between 2 points which have coordinates under your identification, you will just get this quantity in R3. And the same thing in R2 and R1, and I mean R4 you can do this in real life, but it's just the intuitive distance. So if we have the fact that for every point which is closer than some epsilon to a point P, the property holds, then we say that the property is true locally at P. So again, instead of having some interval, now we have sort of an open ball around P. So everything which is epsilon closer to P. So let's look at an example. We can have the property on the real line that number is non-negative. So P of x is true precisely when x is non-negative, and it's false if x is negative. So it's going to be true locally at 1, because any number which is, say, 1/2, so I'm picking as epsilon 1/2 here, close to 1, so anything between 1/2 and 3/2 is going to be non-negative, so we have this kind of interval around 1 where the property holds, so it holds locally true at 1. But while it does hold locally true, it does hold true at 0, it does not hold locally true at 0, because no matter how close we require points to be to 0, there will be always such close points to 0 which are nonetheless negative, which fail the property. So you can kind of visualize this as the following. Here I've visualized the reals as a line, so it should go on beyond the screen here, but just looking at a portion of it, we have the thick dot in the middle, that's the origin, that's 0. And then everything marked, so to the right and the positive reals and to the left the negative, and everything marked in green is which satisfies our property, so it's not negative in this case, so everything which is 0 or right of 0, and everything marked in red is which doesn't satisfy the property, which is false in this case, which is false that the property holds, the negative numbers in this case. So we can also think of this property as kind of this partition of R into two sets. And partitioning a set into two sets, so giving two sets such that disjoint and the union is all of R, is the same thing as just picking out one of them, because the O is going to be the complement of that. So actually we can alternatively think about properties as just subsets. So when we have some property in a set, we can just think about the set of all elements of the set for which the property holds true. And also this is kind of a correspondence. If we have some subset of a set, we can interpret it as a property, namely the property of being an element of it. So in this way, say, the property of integers to be even, we can interpret as the set of the even integers. And okay, this, I mean, a very kind of almost philosophical or kind of very fundamental and silly remark, but actually this allows us to interpret these properties as subsets and interpret what it means to be locally true as a statement relating a point in a subset of Euclidean space in this case, for now. So say we want to talk about a property holding locally true at a point, and again, let's say we are an Rn for now. So n also some natural number, I didn't mention this, but just something like 1, 2, 3, etc., or maybe even 0, that also works here. So if we have some property of points of Rn, we can now think of it as a subset, the set of all points for which it holds true. And now, given some point in Rn, we can ask what does it mean in terms of the subset that the property holds locally at this point. Well, it has to hold this point. The point has to be an element of the subset. Despite that one can ask whether it holds locally for any point, it's only going to hold locally for points which are elements of our subset, of our property in this sense. But also, it doesn't suffice as an element, because as we've seen earlier, we have that for the non-negative reals, which is the example from earlier, our property of being non-negative is identified with the set of the non-negative reals. The 0 is an element of the property in the sense, but it doesn't hold locally at 0. That numbers around it are non-negative. What it needs to require is that there's some epsilon greater than 0, such that every point closer than epsilon to our point P satisfies the property. And so when we write this out in the sense of interpreting the property as a subset of all the points for which it holds true, what we need to require is that this open ball, which I've already mentioned earlier, the set of all points which are epsilon close to P, so one usually writes it as B epsilon P, and here D is just the Euclidean distance, as defined previously. We want that this set for some epsilon greater than 0 is contained in our subset P. And when this happens, and we think of the subset as a property of being an element of it, then this means precisely that the property holds locally at our points. If you do not think of it as a property, intuitively, what this means is the point kind of lies in the interior of the set, and that's where the terminology comes from. Points which satisfy this are called interior points of our set capital P. So then the set of all the interior points is called the interior of our set P, capital P. And whenever we have an interior point of a set, we say that that set is a neighborhood of the point that is an interior point of it. So it's just very useful terminology, maybe a lot of terminology, but it's all quite intuitive, and it's just very common terminology that one might come across, and it's very kind of suggestive and intuitive what it means. And this is just the formal way of interpreting it. So when we say that a set is a neighborhood of a point, we mean that it's kind of, it contains stuff around the point, and what that means is that it contains a ball around the point. And then we say that the point is an interior point. Okay, so in our earlier example, if we take the property of being non-negative, we interpret it as a set. We get the set of all the non-negative reals. Oh, sorry, that's a typo. It's not the non-negative integers, it's the non-negative reals. And its interior, the set of all the points where it holds locally true that all numbers around them are non-negative, is going to be the set of the positive reals. So a proper subset in this case. And so something one might wonder about subsets of Euclidean space is when they are their own interior, and okay, maybe that's kind of an ill-motivated question, why would one care? But often, again, it's very useful to have things be locally around a point. Say in analysis, if you want to differentiate a function defined on a set U, let's say some subset of Rn, then we want that it's kind of locally big around every of its points, so we can take limits. If we have just an isolated point, so say we have a function which has as its domain the singleton 0 union the interval from 1 to 2 in the reals, and then it maps to the reals. Well, we can differentiate it at points of the interval from 1 to 2, but it doesn't really make sense to differentiate it at 0 because we just have a point in the graph instead of a line segment or a curve. We cannot draw a tangent. It needs to kind of to be big around 0. It needs to be in the interior in order for us to differentiate. So if you want to talk about, say, differentiating a function, it has to be defined on a set whose all points are interior. And such sets are called open. So on the next slide will be a nice picture. To illustrate what openness means. So again, we call a subset open of Euclidean space whenever it's its own interior. So whenever around every point of it, there's some ball of some radius epsilon, which is contained entirely within the subset. So let's look at an example. But actually first, there's another very related notion, that of being closed. And that's the same notion, except instead of requiring, when we interpret the subset as a property for it to be locally true, we require it to be locally false. So, okay, what this means, if you just say that a subset is closed when its complement is open, which is this definition, or vice versa, because that's how complements work, one can think of this as, if we think of a subset as a property, then saying that it's closed, or equivalent to its complement is open, means that when we think of its complement, well, what is the complement of a subset that we think of a property as a property? It's the property of being not in the first set, so it's the negation of our property. So we are saying that the negation of our property holds locally at every point where it holds. So whenever the property is false, it is false locally. That's what it means to be closed. So, okay, maybe this is very abstract, but it's actually quite visual. So here we have two sets which look almost identical. And the first one is an open ball in R2, and the second one a closed ball. And so the first one is open, that's alluding by it being called an open ball. And the second one is closed, again, because it's called, I mean, not because it's called a closed ball, but we call it a closed ball in relation to this. And okay, you can see on the picture intuitively what this means is that something is open if it's kind of disjoint from its boundary. This can be maybe formal. You can talk about boundaries as well. We're not going to get into that. This is kind of more technical topological things, or at least it's a different way of viewing things. But you can also think of a subset being open if it's disjoint from its boundary, and closed if it contains its boundary. And this is something you can see visually. So we usually one notates the fact that the boundary is not contained in the set by dotting it, kind of concentrating less of the color there, illustrating that it's not an element of the set. It's just kind of there, it's the boundary. So if we have some subset like here, where the boundary is not contained, well, if we take any point of the subset, it's going to be somewhere in the disk. And it's not going to be on the boundary because the boundary is not an element of it. So there's going to be some space to the boundary. And this space we can take as our epsilon, this distance to the boundary. And then we get some ball contained within it. So we get that this is a neighborhood of all of its points, meaning that its interior is the whole set, so it's open. It's locally big around every of its points. So on the right-hand side, the same is true, but for the complement. Because if we take the boundary of the complement as the same thing as the boundary of what we start with, that's how boundaries work. I'm not defining boundary formally, I'm just using this as an intuitive term. So you can kind of visually see the boundary here is the circle. And so when we look at the complement, the same sort of argument applies. Any point there has a positive distance to the boundary, and we can take that as our epsilon, we get the ball. So whenever something is false, whenever something does not belong to the closed disk, or the closed ball, it does not belong locally in the sense that there's some ball around it that doesn't belong as well. Okay, so these are kind of these very key notions to topology. Really, what topology ends up being about is generalizing these. But actually, how we've constructed these in a RAN, if you want to generalize them, there's a very kind of straightforward generalization one can do before going to the full generality of just generalized openness. Actually, before we do that, just some more examples. If you take the, okay, this is an example that's worth mentioning because with this terminology, one might be led to thinking that every set is either open or closed, but that needn't be. You can have that the boundary intersects the set, but it's not contained within it. This happens with this interval from 0 to 1, which contains 0, but not 1. So it's not open, nor is it closed. It's not open because, well, its interior is everything but 0. It's the same situation as with the non-negative reals. Any interval around 0, any ball around 0, intersects the complement of the set. It's not contained within the set. So 0 is not in the interior, but every other point can be seen to be in the interior. So we get its interior is the open interval from 0 to 1. So it's not equal to its own interior, it's not open, but its complement, it's this set here, it's the interval from negative infinity to 0, the negative reals, then all the reals greater than equal to 1. That's just the complement of the set we start with here. Its complement, its interior is going to be everything except the closed interval from 0 to 1. So in particular, it's not going to contain 1, and again, the complement is not its own interior, so neither the set nor its complement are open, are their own interior. So this set is neither open nor closed. You can also give examples of sets which are both open and closed. So we'll mention an example later. But just to mention that while it might sound like a set is either open or closed, that's not true. These are kind of independent notions. Not fully, because you can make them dependent by talking about complements, but if you don't talk about complements, you can have that a set is both open and closed, open and not closed, not open and closed, and not open and not closed. It's kind of all the possibilities. So generically, in a sense, I mean, this is kind of difficult to make rigorous, but if you just take, so say, a random subset of Rn, it's not going to be open nor closed. These are kind of niceness conditions. So you would expect that a random subset is not nice, so you cannot expect it to be open or closed. But this is kind of difficult to make formal, though it can be made formal with things like the Vittori's topology or bare categoricity, but these are technical notions kind of too far afield here. So, okay, another thing to mention before we get to abstracting things away, because in order to abstract things away, we would like to see some properties of openness. And in this case, this is a property of taking the interior. So above, we've observed that in the case above, with the complement, the union, so the complement above is a union of two disjoint sets, and its interior is the union of their interiors. This is generally false. So just not to be led to thinking this, here it's mentioned, in general, we do not have the fact that the union of two sets, the interior of that is the union of the interiors. So if you take, say, these sets are not disjoint, we can make them disjoint in the right setting. If you take the sets from -1 to 0 and from 0 to 1, the closed intervals in the reals, well, the union is the interval from -1 to 1, and its interior is the open interval from -1 to 1. But it's not the same thing as the open interval from -1 to 1 removed 0, which is the union of the interiors. So this illustrates that in general we cannot compute interiors with unions, and this is not too important of observation, but this is just kind of to mention here to kind of see what these notions behave like. So note also that if we have a subset, if you have a set A contained in a set B in the Euclidean space, then the interior of A is contained in the interior of B. Why? Because if we have a point of A, so a point of the interior of A is going to be in A and it's going to contain a ball around it within A. And then this ball around it within A is going to also be within B because B contains A. So in particular, it's going to contain a ball around it within B, so it's going to be in the interior of B. And so we note that A is a subset of the union of A and B, and B is a subset of the union of A and B. So both the interiors are subsets, and so the union of the interiors as a union of subsets is a subset. So we have this inclusion always. Okay, so these are just kind of random properties to illustrate what these notions behave like. So kind of the most general properties in a sense we can extract from openness, not from interior taking, but from openness. It's kind of a more standard way of doing things. So you can abstract the notion of taking interior, or you can abstract the notion of openness. And if you do things properly, they're going to be the same abstraction. But it's very standard to abstract the notion of openness to define the general notion of space, topological space. Because again, what one does in topology, one has these notions of locality and Euclidean space, and one wants to abstract them to a more general setting to talk about locality in over context, even when one is in Euclidean space, say one is saying something true locally about all functions near a function. This is also a very useful thing to talk about, and one has things like the uniform topology, or has things like the compact open topology, which are a way of doing that, which we'll get to in a moment. Not these specific topologies, but the general notion of how to do that. But for that, one needs to abstract things, and for that, one needs to choose what to abstract, which notion, which properties. And so instead of abstracting interior taking, one usually abstract openness. And kind of the most important properties of openness one can see are the following, or most important, at least the ones that one abstracts. One has that the empty set and all of Euclidean space are open within Euclidean space. Now, okay, it might sound kind of silly if we say that the empty set is open, or the whole space, whole Rn is open. But if you just apply our definition, well, the empty set has no points, so this neighborhood of all of its points kind of vacuously, which again, somewhat silly, but strictly speaking, this our definition applies. And all of Rn is open because, well, any of the points of Rn has a ball around them contained within Rn, because, well, any ball is contained within Rn, because we're taking balls within Rn. So Rn is a neighborhood of all of its points, so it's open. So you get these two sets, and this is also an example of sets which are both open and closed. So sometimes they're called clopen. It's kind of, again, silly, but that's actually standard terminology. Because, well, the complement of the empty set is all of Rn, and vice versa, and both of them are open, so also both of them are closed, because their complements are open, because their complements are them, and they are open. So we get two sets, and they're both clopen. Actually, in Euclidean space, it's the only clopen sets, and saying that they're the only clopen sets in the general context is a very geometric thing. It's called connectedness, which we'll not get to, but to just kind of to illustrate also what sort of things one can do in general spaces, which we'll come to in a second. So that's the first property that one likes to abstract. The second one is that if you take two open sets, their intersection also is going to be open. Now, why is that true? Well, if you have a point, so suppose A and B are open, if you have a point in the intersection, well, it's also in A because it's in the intersection. And so there's some ball around it in A. And it's also in B. And then there's some ball around it in B because A and B are open. And so we have two balls around it, one in A, one in B. Well, the intersection of two balls around the point is a ball again around the point, the smaller ball around the point. And so this ball is going to be contained in both the balls, so in A and in B. And so we'll get a point in the intersection, or a ball in the intersection of A and B. And so we have that there's a ball around, or point, which is in the intersection of A and B, meaning that A intersects B is a neighborhood of all its points, so it's open. Okay, so that's the second property we'd like to abstract. The last one is that if you take an arbitrary collection of open subsets of Rn, take the union, so a set of all the points which belong to at least one of the sets, this is also going to be open. And I mean, the argument is again similar. We take some point in the union, and then it's going to lie in one of these sets, in one AI for some I and I, or multiple, but at least one. And so because AI is open, by assumption, there's some ball around a point contained in this AI, but then this ball is contained in the union, so again, we get the ball in the union, so the argument proceeds the same. So we have these properties of open subsets of Euclidean space, and actually this is already what one just abstracts straightforwardly and gets the notion of topological space. But before we do that, it's something I already mentioned kind of earlier, kind of prematurely. There's this more kind of intuitive thing one can abstract, just distance, which allows to construct many examples of topological spaces just the same way as we've done with Euclidean space. And so the notion is that of a metric space, and it was introduced by Felix Hausdorff in 1914. Actually, Oh, I'm sorry. I forgot my order of my slides. So first, okay, metric space is the next slide. But actually, Felix Hausdorff introduced both relevant notions of space, um, at least to topology here, metric and topological spaces. So first, let's abstract the things on the previous slide. Okay, it does make sense. And there's a typo already here. So actually, okay, what are we doing here? We've seen the notion of openness in a Euclidean space in Rn of subsets, what it means for subsets to be open. And we've seen some properties of it, and we can just straightforwardly generalize these properties, abstract them away, and then get a notion that we can talk about. And the notion is that of a topological space. Okay, we can generally say, we'll replace Rn by some arbitrary set, and then we want to define what it means for subset to be open. Well, whatever it means for it to be open, we want the same properties to hold. And so we just take the same properties, and I've actually took them too much, because instead of requiring that the empty set n are in the collection of all of the open subsets, which is what we'll abstract away. We'll be abstracting away open subsets. So in order to abstract them away, we have to determine, we have to decide which subsets of our set we'll call open. And so we can just say that we take the set of all. So what we're giving our conditions on is this decision process. We want to decide which ways of deciding which subsets of X are open are valid. And so a way of deciding which subsets of X are open, the same thing as our properties earlier, is just a set of subsets. So a collection of subsets. So such collections called topologies. So say we have some collection of subsets T of X, and we want to think of it as the collection of all open subsets of X. So its members as the open subset of X. And so we want to require on its members the same properties as earlier, so that the empty set is a member, and that the whole space X is a member, and so it shouldn't say Rn here, it should say X. And we also want to require that the intersection of any two members is a member. So again, being a member of this collection, we just think of as a generalization or abstraction of being open. So we want that the intersection of any two open sets in X is open, so any two members of T is in T, and also the union of any family of members in T is in T. And when we have this collection of subsets of a set X satisfying these properties, we call it a topology. And jointly, we call a set together with such a collection a topological space. And then one calls the elements of our set X points and the elements of our topology open subsets of our topological space. And their complement is closed subsets. In fact, we can also define the notion of interior, which I'll mention the definition of in a moment, and kind of do all of the same things we did in Euclidean space so far, essentially. So we can also talk about locality, which is why this notion turns out to be quite useful, despite kind of abstracting away this unintuitive openness. I mean, maybe it is intuitive, but it's perhaps not somewhat unmotivated. So in particular, because we've abstracted things away from Rn, Rn itself is an example of a topological space. And so we have to decide which subsets of Rn are open, which are the members of our topology. And they will just be the subsets open in the sense defined previously. Subsets such that around every of their points, there's some ball contained within them. Ball under the Euclidean distance. What I mean by under the Euclidean distance, well, this is what I was talking about prematurely twice already, notion of a metric space, because we can abstract away the notion not only of an open set, but of the distance function. And we can get this collection of openness, this collection of open sets, this notion of openness and locality from a distance, because that's what we did with Euclidean space. We said that a point is in the interior of a set, whenever there's some ball around it, some epsilon greater than 0, such that all points closer than epsilon to that point are in our set. And whenever we have this notion of distance, we can give the same requirement. So actually, it suffices to abstract the notion of distance, and we get a stronger abstraction in the sense that we have for any abstraction of the notion of distance an abstraction of the notion of openness. Okay, so maybe I'm talking all wishy-washy here, but what I mean here, again, Hausdorff in the same year, 1914, defined the following. Also, actually, well, let me first mention this. He defined the following notion of a metric space, which is just a set together with a notion of distance between 2 points of the set, which one again abstracts away some properties of the distance function in Euclidean space, namely these. The 2 points have a distance of 0 whenever they're equal. The distance taken is symmetric, so the distance from x to y is the distance from y to x. And also something called the triangle inequality, the fact that the distance from any point to any point x to point z is less than or equal to the distance from a point x to another point y, or equal to actually just some point y, and then plus distance from y to z. So you can visualize this if you draw into plane a point to x and then a point z, and then you also take some point y, if you take the distance from x to y, and then from y to z, well, we've kind of drawn a triangle. This is going, the sum of their distances from x to y and y to z is going to be no less than the distance from x to z. So kind of distance taking is optimal in this way. So again, we get these functions known as metrics, and we get a notion of space, that of metric space, as set together with a metric. And what I was mentioning earlier is that this definition is present in Felix Hausdorff's 1914 book. But the previous one on the previous slide is not quite present in the same way. It's present in a similar way, in a slightly altered version. So actually, we've abstracted away the notion of openness, but again, there's a great deal, a great variety of ways of getting the notion of a topological space. Instead of abstracting the notion of openness, we could have abstracted the notion of taking an interior. And it would have been equivalent. Whenever we have an abstraction of a notion of interior, we get an abstraction of a notion of openness. A subset is open whenever it's its own interior. And vice versa. We can, given a topology, define what it means to take the interior of a set, which we'll get to in a moment, as said. But also, what one can do instead is abstract the notion of so-called closure taking, which I'm not going to define anyway in this talk, but it's related to taking the interior. And this is what Hausdorff did. He thought about topological spaces instead of closure taking, and he had one additional assumption about topological spaces, which we do not impose usually, kind of get a more greater generality of topological spaces, which turns out actually very useful in algebraic geometry, which we'll get to in a moment as well. But okay, again, where are we? We've thought about the notion of locality, and we've noticed that we can talk about it in terms of this distance. So saying that we've talked about locality of a property holding true locally at a point. And then we've abstracted properties to subsets, and then talked about a point lying in the interior of a subset as the property holding true locally at the point, when we think of the subset as a property. And then we said that let's call subsets who are neighborhoods in the sense of, well, the neighborhoods of all of the points, so all of the points lying in the interior, neighborhoods in this sense. Let's call them open. Look at the properties of openness and abstract them away. We got the notion of topological space, but actually the way we started to begin with, defining open subset of Wheaton space, right, and taking distance of points, taking these balls, we can do this also and get these metric spaces. And whenever I have a metric space, we can do the same thing and define a topology, define what it means to be close or locally around a point. Just say that we take all of the points closer than some distance, and that we want to have this set, this open ball, lie in a subset for a point to be in its interior. So whenever we have a metric space and some subset, we can define, again, a notion of interior just by the same definition, saying that a point is in the interior of a subset whenever there's some epsilon greater than 0, such that all points closer than epsilon, now d is not the Euclidean distance, but just some arbitrary distance, some metric, lie within the subset. And then again, we get a notion of openness. We say a subset is open whenever it's a neighborhood of all of its points, whenever the interior of it is itself. And then we get topology. So this is not I mean, it's a straightforward fact, but something to verify. When we start with the metric, with these assumptions, we get the assumptions of a topology. The fact that when we define openness by this, the union of two open, or the intersection of two open sets, or union of an arbitrary family of open sets is open, and the empty set is open, and the whole space is open. Something you can do as an exercise, say. And so whenever we have a metric space, we get a topological space. And a natural question to ask is whether every topological space arises from metric space, and that's not true. So the ones arising are called metrizable. But there are examples of non-metrizable ones. And to look at some of these examples, because these examples are quite relevant to algebraic geometry, because almost all spaces one encounters there are non-metrizable. One has a different notion of locality that one utilizes, one not arising from distance. So one notion to look at to detect non-metrizability is that of being Hausdorff. And this is the property which Hausdorff originally required all topological spaces to satisfy, which one then dropped to have a greater generality of topological spaces to also utilize topological terminology in, say, algebraic geometry. And okay, what does it mean for a space to be Hausdorff? So this is also the reason this property is called Hausdorff. It's also referred to being as T2 sometimes. So one would say the space is T2 or Hausdorff, same thing. What it means for space to be Hausdorff is specifically that for any two distinct points, the points have to be distinct of our space, there are some open subsets. So it's a topological space you're talking about. It makes sense to speak of open subsets because a topological space is given by specifying which subsets are open, taking a collection of all some subsets which one calls open. And so we can talk about open subsets, and then that space is housed off whenever given any two distinct points, the disjoint open subsets around them. So disjoint open subsets containing one, the first point, and second to over. So maybe, okay, I'm not putting it well, it's written out here, but also there's a picture we can draw. So let's imagine X is some blob, so space, and we have 2 points P and Q, they're distinct. Well, what we're requiring for it to be housed off is that we can find some two open sets, U and V. They're disjoint, they have no common points, and U contains P and V contains Q. This is this condition that originally Hausdorff required in his definition that one can see to be true for all metric spaces. In particular, we can use to detect non-metrizability. So how do we see that in any metric space given two distinct points, there are open subsets of the metric space such that disjoint and one contains 1 point, the second to over? Well, it's also a fun exercise, but let me just sketch the proof verbally. What you can do, let's say you have 2 points P and Q, and we're in a metric space, so there's a distance between them. Let's halve the distance and take open balls around P and Q of that radius. So then you can kind of visually imagine the case of, say, R2, we have these two open balls. Now, in R2, they're going to be open disk. And you can prove with the help of the triangle inequality the disjoint. And one can also verify something that one needs to verify, that open balls in metric spaces are open. So it's clear that they are a neighborhood of the center point, because by definition, we say that the subset is a neighborhood if there's a ball containing a neighborhood of a point if there's a ball containing the points at center such that it's contained in a subset. And so for a ball, we can just take the ball itself as this ball. But for the other points, we have to take other balls, and again, there's something to verify. It's kind of also very geometric, so it's something fun to do, I would say. But so this is one way to see the property in the general metric space. Take 2 points, we can separate them by disjoint open subsets by taking as our open subsets just open balls of radii half the distance between the points. But this allows one to already get a large family of examples of non-metrizable spaces, because we know that any topological space coming from metric space will be Hausdorff. And so, for example, one can just very explicitly write down a topological space like this. This is something very fun to do, though these spaces aren't very geometric. But on any finite set, one can just explicitly enumerate all open subsets, all subsets one deems open, as long as they satisfy the properties of a topological space, the properties of the topology, so that they are closed under taking intersections and finite intersections and arbitrary unions. In this case, it's the same thing, because finite or not, because we're in a finite space, so there are finitely many subsets, so there isn't an interesting infinite union one can take. So whenever this is true for our collection of subsets, and whenever it contains the empty set and the whole set, we get a topology, and so in particular we can say, take this. So here I've drawn 0, 1, 2, 3, so points of the space, and all of the non-empty open subsets as blue blobs. So we have the singleton 0, 0, 2, and 0, 1, 2, 3. Now, of course, we also have the empty set, but I didn't draw that, just because there's no point. I mean, I suppose I could have also omitted drawing the whole space, because we know that it's open by definition, but this is what one has. So we know that this is not a metrizable space. Why? Because it's not Hausdorff. And we've seen that all metric spaces are Hausdorff. Why is it not Hausdorff? Well, let's take the points, or set points 2 and 3. Let's take the points 1 and 3. It's even easier to see. There are no open subsets that is joint, and one contains 1 and over 3. Why? Because there's only one open subset containing 1. It's the whole space, and same thing for 3. So any two open subsets containing 1 and 3, they're simply joint. They have the whole space, and so they intersect. So this space is not Hausdorff, so it's not metrizable. So what this illustrates is that this abstraction of openness, of interior taking, it's a more general thing than the abstraction of distance taking. When we specify what the distance between points are, we specify what it means to be close to something, or what it means for something to hold locally, but the converse is not true. If we know what it means for something to hold locally, there isn't a distance we specify. We just know what locality means. So it's actually a vastly different notion. So another example we can take on any set now, doesn't need to be finite, we can take the industry topology. And that's just topology where we declare that a subset is open if and only if it's empty or the whole set. And so it's the smallest topology possible in a set, the coarsest, which we'll get to in a moment. And it's also not Hausdorff unless the space contains at most one point, because any two distinct points will have the same problem as above with 1 and 3. There's only one open set containing either of them, the whole space, and the whole space is joined with itself, so it's not housed open, not metrizable. So just let's see another example of a topology, and that's of the discrete topology, and that's a metrizable topology. Given a set, we can take the discrete metric, which assigns 2 points distance of 0 if they're equal, as it has to, by the axioms of metric we require, and assigns the distance of 1 to any 2 distinct points. So it's kind of a very coarse notion of distance. We say that distinct points have a distance of 1, and equal points have a distance of 0. So all the distance tells you is whether 2 points are the same or not. It's kind of boring, but this is a valid notion of distance taking, at least in the sense of our abstraction of metric spaces. And one can look at what open subsets under this topology are, on this metric, the topology induced by this metric. In fact, it turns out that every subset is open. Now, the way to see that, well, we can see that any open ball of radius 1/2 around the point is going to be just a point. Because any other point except the point has a distance of 1, so it's not in the ball. And the point itself has a distance of 0 to itself, so it is in the ball. And so we get that singletons are open balls, and as you can check, open balls are open, so singletons are open. But arbitrary unions of open sets are open by the assumptions of topology. And if you can, since you can verify that the open subsets of a metric space under the induced topology indeed define a topology, the induced topology is a topology, we get that arbitrary unions of singletons are also open under the discrete metric, and so we get that every subset is open. So the collection of all subsets is called the Pau set, and so in this case, the Pau set is the topology we get from the discrete metric. Another example. And these two examples, the indiscrete topology and the discrete topology is the Pau set, the one we get from the discrete metric, they actually turn out quite illustrative examples of a more general phenomenon of something to do with looking at sizes of topologies and something giving a very rich plethora of examples of topologies. Also, the most important topology we'll see for algebraic geometry will also be an example of this sort of construction. But again, I'm kind of jumping ahead. So next, let's turn our attention to something called continuity, which one often sees in a more elementary context, in a less abstract context, less generality. But you can actually interpret it into this general context of topological spaces, because really continuity is also about this notion of locality. And we can have the notion of locality in any topological space. So let's look at this function from R to R, and it's just squaring, except starting at 1, we add 1. And so the function kind of has something happen at 1, where we can notice that there's a sort of jump in the graph. And formally how we can capture that is by saying that we cannot control how close points are to the value at 1 by controlling how close they are to 1. So in other words, if we want that points are locally close or are close to 2, the value of this function at 1, there is no locality at 1 which maps into that. There's no neighborhood of 1 which maps to an open ball containing 2. So let's try this out. We can interpret the fact that f is discontinuous above as the fact that, at the point 1, as the fact that no matter how close we want to be to f of 1, there is no interval around 1, such that every value of our function around 1 in this interval is mapped 1/2 close to 2. So 1/2 is just an example number. You can take any number which is less than 1 in this case. So this is kind of something we can interpret in a general topological setting, again, by the notion of locality and openness. Because really, what one is saying, the fact that one is closer than 1/2 to 2 under the value of the function isn't a fact holding locally true at 1. So let's write this out as a definition. If you have metric space x and y, so for now I'm writing this in terms of metric spaces because this more clearly illustrates how the notion of abstract, but actually we'll abstract it to the notion of topological spaces, continuity of maps between topological spaces in a second. But just between metric spaces, if you have a function between metric spaces and a point of the domain of this function, then what it means for this function to be continuous, we can define to be that for every epsilon greater than 0, the property that the distance of the value of the function at the point is closer than epsilon to f of p, this property holds locally true at p. So again, what does it mean to hold locally true? In our sense, this means that there's some number, well, we usually say epsilon, but now if we already use epsilon, it's called delta, some number delta greater than 0, such that for any point delta close to p, this property holds. So in other words, what it means for f to be continuous at the point p of x in this sense is that there's some delta greater than 0, such that any point delta close to p maps to epsilon close to f of p. For any epsilon greater than 0, we can find such delta. That's what it means to be continuous at a point. So continuity we've defined here at points. As the example before illustrated, the only place where the function had some discontinuity in a sense was at 1. Everywhere else it just kind of looks like a parabola. So because of that, continuity is usually defined at points, but we can also just extend continuity to be global by saying that the function is continuous, period, if it's continuous at every point of its domain. So it's kind of a straightforward generalization. And so notice that, again, we're talking about locality, we're talking about being close to P, implying that one is close to f of P. And being close to f of P just means lying in the neighborhood of f of P. At least one can take it to mean that. And when one takes that to be the case, one gets the abstraction to the topological space as mentioned. So what it means to be epsilon close to f of P just means to lie in the open ball of radius epsilon or f of P, and that's the neighborhood of P. And conversely, any neighborhood of f of P contains some open ball around f of P, of some radius, say epsilon. So really, we can rephrase the above just in the setting of metric spaces as saying that a function f is continuous to the point P of x, where x and y metric spaces, and f is from x to y, again as above, whenever the preimage of f under any neighborhood, preimage of f of any neighborhood of f of p is neighborhood of p. So the fact that f of q is epsilon close to f of p can be took to mean that f of q is in the neighborhood of f of p, defined by epsilon, and we can just abstract epsilon away to any neighborhood. And then when one is saying that the set of all q satisfying this is a neighborhood of p, one is just taking the preimage and saying that the preimage is the neighborhood of p. So we can just kind of reread this in terms of this notion of openness and neighborhoods, and give the following definition in a greater generality. So for that, one first needs to define neighborhoods in topological spaces if one wants to generalize topological spaces. And then, I mean, as I said, it's equivalent to defining openness. We can just say that a point is in the interior of a subset of a topological space. Whenever there's some open subset of our topological space, which is within this subset that we are talking about being the interior of, and contains the point. So whenever we have this inclusion, P is an element of U, which is subset of A, and U is an open subset of X, then we can say that P is in the interior of A. And then we can say that A is in the neighborhood of P. So we just kind of do the same terminology as in Euclidean space or metric spaces, that a point is in the interior of a set whenever the set is the neighborhood of the point. And so we get this notion of neighborhood in any topological space. Again, it's equivalent. We could have chosen to generalize a great many things. We could have generalized openness as we did, or closeness, or interior taking, or closure taking, which we've not defined, or we could have generalized boundary taking. There are many equivalent ways of doing this, and actually it's kind of interesting to see if you look in different topology books, sometimes the way they pedagogically approach topological spaces is by generalizing different notions. So again, Hausdorff originally generalized closure, but usually nowadays one generalizes the notion of openness, but still equivalent, at least if one does it as standardly done. So we do have the notion of neighborhoods in any topological space. And so because of this remark of rephrasing the intuitive definition of continuity for metric spaces, we can actually interpret continuity at a point in any topological space, in between any topological spaces. If you have topological spaces x and y, and a function from x to y, and a point p of x, everything as above except now x and y are topological spaces, then we can call f continuous at p, provided the preimage of any neighborhood of f of p under our function is the neighborhood of p. Then again, we can say that f is continuous if it's continuous at every point of its domain. So we kind of just generalize notion from earlier to this setting. And okay, it might seem like just generalization for the sake of generalization here, but actually it does turn out that in many, especially algebraic geometric settings, this more general notion of continuity, allowing to talk about continuity for notions of being close to or holding true locally, which are different than ones arising from the notion of a distance, turns out to be very useful. Again, in many settings, such as algebraic geometry, we'll see. I mean, this is the whole reason I'm giving this talk, to motivate, kind of illustrate where these notions come from, in the setting of algebraic geometry where we'll be doing exactly this. Okay, so this notion of continuity we get. So one very common way of rephrasing continuity globally between topological spaces and consequently also between metric spaces is the following. Namely, that the function between topological spaces is continuous whenever the preimage of any open set, now not the neighborhood of a point, but just any open set, is an open subset of the domain of the function. The open subset of the preimage of any open subset of the codomain is an open subset of the domain. So really all we're doing, because we are, instead of looking at continuity locally at a point, instead of taking neighborhoods of f of p for some point p, we're just saying, instead of neighborhoods, let's take open subsets of our codomain. So sets which are neighborhoods of all of their points. When we take the preimage of them, well, they should be neighborhoods of all of their points in the preimage. So we can prove this because we have the definition in terms of neighborhoods. So let's first prove that if we have a continuous map between topological spaces, in the sense that, in terms of neighborhoods, then the preimage of any open set is open. So let's take some open subset of y and some point in its preimage. Well, then the value of the point under our function is going to be in this open subset of y because we took it into preimage, the point. And because this open subset of y is open, it's a neighborhood of f of p, where p is our point and f our map. Why? Because, well, f of p is an element of u and u is a subset of u. So you have the same sort of inclusion as above, and that's how we define neighborhoods in arbitrary topological spaces. But because f of p is an interior point of u and u a neighborhood of f of p, we know by the definition of continuity, because f is continuous at p, because it's continuous everywhere in our sense, we have that u is a neighborhood of f of p, so the preimage of u is a neighborhood of p. So in particular, it means that p is an interior point of the preimage. So we've shown that all the points of the preimage of u are interior points of the preimage. So the interior of the preimage is the preimage, and so the preimage is open. So here I'm kind of sweeping under the rug some of these notions because we've not quite cleanly proven that a subset of a topological space is open if and only if it's a neighborhood of all of its points, but you can verify that because if it's a neighborhood of all of its points, well, then there are open subsets around all of the points of it, then you can take that union. And conversely, if you have an open subset, it's a neighborhood of all of its points, as we've seen here in the proof. So hence you see that any continuous function takes open subsets of the codomain to open subsets of the domain. So let's take the converse. If we have an open subset of the codomain of a function, actually no, sorry, we're going to over directions. Now we have a point of the domain of a function in topological spaces, and this function takes preimages of open sets in its codomain to be open in its domain. We want to show that given a neighborhood of its value at this point p, so given a neighborhood n of f of p in y, we want to show that the preimage of this neighborhood is a neighborhood of p in x. So because n is a neighborhood of f of p, by definition we know there's some open u in y, which is contained in n and contains f of p. Because by assumption, the preimage of u is open, and f of p is in u, there's a typo, sorry, I should say p is in preimage of f of u, and it's contained in preimage of f of n because taking preimages is monotone. If a is in b, the preimage of a is in the preimage of v. Because if something maps to A, then it maps to B if A is contained in B. And sorry, yes, there's a typo that should say thus P is an element of the preimage of U. And so by definition, we get that the preimage of N is a neighborhood of P. And so F is continuous at P, and this holds true for any point P of X, so F is continuous in all previous sense. Okay, so this is kind of a way of phrasing continuity globally as this one condition. It's just a very common and general way of viewing continuity that one might come across so often. Instead of doing the whole intuitive discussion of continuity from looking at the graph of x squared if x is less than 1 and x squared plus 1 if x is greater than equal 1, one just straight gives this definition without really elaborating why one defines continuity this way, and it might seem kind of unintuitive, but really we're just kind of coming from this usual intuitive notion that we can control how close points are in the codomain by controlling how close they are in the domain. The fact that being close in the codomain is a local property in the domain. That's what continuity intuitively means. That's how it's reflected here in this more general context. So some useful things to verify. Compositions of continuous maps are continuous. So I'm not going to verify them here, but it's just good to know. And also, this makes the class of all topological spaces what's known as a category, which allows us to immediately talk about a great many of concepts. I'm not going to talk about this, but this is good to know. And for example, one of the concepts one gets is that of a homeomorphism. So actually, this remark is a very good exercise for using this above lemma. It follows quite straightforwardly. a homeomorphism is just kind of an isomorphism of topological spaces in the sense that it's a bijective map of the underlying sets, such that open sets map to open sets, and the primitives of open sets are open. So actually, it's just a continuous bijection whose inverse is also continuous. You have to be careful. With algebraic structures, if you have a bijection, which is a good map in the sense it's a homomorphism of rings or of groups, then its inverse is also a homomorphism. But with topological space, that's not true. You have continuous bijections whose inverses are not continuous. It's also a nice exercise to find one. So it's just a good term to know. You might come across it. Let X is homomorphic to Y. What it means is just that they behave the same way when concerns looking at points locally and continuity. There's a bijective function which renames the points from one set to the other, such that open sets map to open sets and vice versa, open sets come from open sets. Okay, so now having discussed continuity, we can move on to a very big family of important examples of topological spaces, which is how I also want to tie kind of into the algebraic geometry and motivate the topology in the algebraic geometry to come. So that is the notion of a weak topology. And for that, we have to mention what it means for topology to be finite and novel, constant novel. And I've already kind of mentioned it when talking about indiscrete and discrete topologies. So what we can do when you have two topologies in the same set, you can kind of compare them because they're on the same set. It doesn't really make sense to compare topologies in different sets. At least it's not straightforward unless you have some sort of function between the sets. But if it's on the same set, well, we can just think of the topologies as collections of subsets. They are subsets of the power set, so they're subsets of the same set. And we can think about them being contained in each other. So we say that a topology is coarser than another whenever it's contained within it. So just because this containment kind of can get confusing because we're taking containment and rewarding that into words, TC is contained in TF whenever TC is coarser than TF and TF is finite in TC. So being coarser means containing less open sets, being finite means containing more. It kind of makes sense intuitively. That's where the terminology comes from. If you are coarse, you have not many open sets to talk about. If you are fine, then you have many open sets to talk about. So you can kind of differentiate more. Now, careful, when I said the discrete metric, I said it's very coarse. Actually, the topology we get from the discrete metric becomes very fine. That's just kind of a coincidence. It's a different notion for coarseness of metric, the one I mentioned earlier, just so you don't get confused about that. But indeed, we have that the indiscrete topology is the coarsest of all of the topologies in a space, and on a set, and the discrete topology the finest, because well, the indiscrete topology contains the empty set and the whole set. That's all, and any topology has to contain that. So the indiscrete topology is contained in every topology in the set, so it's the coarsest. And the finest topology, well, it's the power set because every topology is a collection of subsets, so it's a subset of the power set. So we have these notions, and actually, we see that the indiscrete and discrete topology are kind of coarsest and finest, and that's something we can do generally. So we can take coarsest topology with the property, and that gives a way of constructing many examples of topologies. So one thing one can extract from this is what is called taking a weak topology. For that, we take some set X and some index set I, and for every element of our index set, for every index lowercase I, we take a topological space yi and function fi from x to yi. Okay, so that's a lot of things going on, but really what we have is just some set x, and then we have functions out of x into topological spaces. So x is an abstract sense, but out of this abstract set, we have functions into like concrete real things in topological spaces, like into real numbers, or maybe R4 or the integers, which one can do as a topological space, as a boring one, as a discrete space, or some other topological spaces. And having all of these functions, because they go to something topological, we can hope to induce topology in X. And one can do that, and that's called the big topology with respect to this family of functions. And the way one does this, one wants all of these functions to be continuous, and one can achieve that with many topologies in X, but we can take the coarse topology, which has this property. So the topology T on X is called the weak topology with respect to a family of functions if one, all of the functions are continuous with respect to it, and two, it is the coarsest topology with this property. So it is coarser than any other topology with this property. Now you will have to prove that it exists, but actually it's quite easy to prove. It's kind of a process of generation. What you can do, well, for all of these functions to be continuous, as I've seen, we need to take all of the preimages of open sets to be open. So we can just take the preimages of all the open subsets of yi under fi for all I, and we get a lot of open subsets, or we get a lot of subsets of x, and we declare them to be open, and then we add all of the subsets which we need to get the rest of the open sets. We take the finite intersections, take the arbitrary unions. And this way we've generated topology on X. And actually, because of how preimages work, this turns out to be quite well behaved if we only take one function, say. But for many, yes, we just have to intersect and take unions. And yes, we get a topology in X, and it is the weakest, it's the coarsest with the property of all of these functions being continuous, because whenever these functions are continuous for topology on X, well, all of the preimages of the open sets are going to be open in X, and so all of the combinations that we can do in the topology of them, finite intersections, arbitrary union, also going to be in topology on X. So our weakest topology as constructed is in the topology on X that these functions are continuous with respect to. And also, with respect to the topology we constructed, all of these functions are continuous because, well, we kind of constructed this way. So indeed, this is a kind of a concrete way of thinking about the weak topology. We just take the preimages of all the open subsets and carry them over back to our set. And this allows to formulate many examples of topological spaces very conveniently. So for example, something one can write out explicitly, but then also interpret in this way. So we have some topological space and subset of it. Well, ideally, we're in a space, kind of a geometric thing. We also want to interpret a subset as a geometric thing, and we can do that. We just take the weak topology with respect to the inclusion. So what this means explicitly, we take the open subset of A to be the preimages of the open subset of X under the inclusion. But what are the preimages under the inclusion? They're just the intersection with A, right? If you have some subset of X, and we take the preimage of this subset under the inclusion of A into X, we just take the set of all elements of A which map into set. So just the intersection of A with the set, because the elements of A map to themselves under the inclusion. So just we're asking that they are equal to elements of the set, just all elements of A which are also in this set. So A intersected the set. And so because we just with one function, we don't have to generate anything. We already get a topology. And this topology is called the subspace topology on A from this inclusion. So another example, let's say we have some set X and we take all the functions to 0, 1, the two element set, and we want to view it as a topological space to take the weak topology, to induce the topology back on X, and we just take the discrete topology. So we take the subspace topology of the Euclidean topology in R. This turns out to be discrete because, well, the distance from 0 to 1 is 1, and basically we, again, back with the discrete metric. It's the same argument. We can take open balls and they'll be singletons. Any finite metric space turns out to be discrete. And this is the topology that induces as discrete. Because, well, again, singletons are balls, and then our argument works out as earlier. So if we take all of the functions from a set X to a discrete space with two elements, and we take the weak topology on X, we just get the whole discrete topology on X, the largest topology, as the weak topology. So now it's kind of funny. We're taking the coarsest topology with respect to which all of these functions are continuous, and we get the largest topology, the finest topology. Why is that the case? Well, because we've took all the functions to be continuous, and so for all of them to be continuous, the preimages of all the subset of 0, 1 under all of these functions have to be open in X. So basically, all of the sets in X have to be open because any subset of X can be seen as the preimage of a function to 0, 1 of, say, singleton 0 or singleton 1. You can take so-called characteristic functions, say. And singleton 0, 1 is in 0, 1 open because 0, 1 is discrete. So we get the whole power set in X. This is another example of weak topology. There are many other topologies we construct weakly. And something worth mentioning, dually, taking the coarsest topology, we can take the finest, but actually, if we take the finest here, we will always get the power set, because, well, if you have the discrete topology on a set X, and then a function out of X into a different topological space, the preimage of any open set is going to be open in X, because every subset is open in X, because the topology is a power set, it's a discrete topology. So it doesn't really make sense to take the finest here. We're taking the coarsest for a reason. What one can do instead, one can consider functions out of topological spaces into X, reverse the arrows, and then we take the finest 10, and that's called the strong topology. That's also an important class of topologies one gets. So these topologies, the weak and strong topologies, respect to various families, for example, very useful in functional analysis, but also in algebraic geometry, as you'll see now. So what I want to talk about at the end of this talk is how we can induce a topology in a general algebraic setting for which we can use this notion of weak topologies. But before, let's talk about the confined topology in any set. As an example we'll just need in a moment. So given any set, something that happens in host of topological spaces that singletons are closed, also in metric space, because metric space is housed of. So for example, in Euclidean space, take a single point, it's going to be closed. Intuitively, it's its own boundaries, it contains its boundary. And any point outside of it has some distance, and you can take the ball of radius that distance, and we'll get that the ball is contained the complement is open, so the singleton is closed. So what one can naturally require is that, let's say we take all topologies in a set where singletons are closed, and let's take the courses of them. We can always take the course topology of some collection of topologies in a set. We can intersect the topologies. We can verify that that's also topology. And what one gets is called cofinite topology. Why is it called cofinite? Well, we've declared that singletons are closed, and we know that the finite intersection of open sets is open. So by De Morgan's law, a finite union of closed sets is closed, because the closed sets are the complements to open sets. So we know that any finite set is closed in our set X, and again, this is something true also in any Hausdorff space. But these are really all the sets that we are requiring to be closed, and the complement is requiring to be open. So a subset now is open whenever its complement is closed, whenever it's finite. But actually, I've forgotten to mention something. Of course, the complement of the empty set in general is not finite, because it's going to be the whole set. But we also require, of course, the empty set to be open in X. So the cofinite topology in a set X is just a topology whose open subsets are the empty set, and all the subsets whose complements are finite. So it's kind of the closest topology one can prove, such that all the singletons are closed. Now what one can do, one can, on any field K, impose the cofinite topology, because it's something intuitive. If you want to get a topology on general algebraic setting, and we're just on a field, well, we can topologize the field by just saying that the singletons are closed, and that's it. But now, let's go a dimension higher. With Euclidean space, we often go with the real numbers, we often go to Euclidean space, to Rn. So let's go to Kn. Let's replace the real numbers at the field K. And what we can do, we can induce an interesting topology on Kn. We take on K the cofinite topology. So we just say that the points are closed. It's something natural to require. And then we take all the polynomial mappings from Kn to K, which is kind of a natural family of maps, which in the case of K equals R, are all continuous. And then we say that just take the weak topology on Kn with respect to the set of all the polynomial maps from Kn to K, viewing Kn as the cofinite topology. And we get the topology in Kn is known as a risky topology. So intuitively what this looks like in Euclidean space, if we take K equals R and N equals 2, we do not recover the Euclidean topology, we get a different topology. This topology is quite coarse, because we took only some of the continuous functions to K, if K equals R. We took only the polynomial maps. So really not that many functions. So for example, of course, usually under the Euclidean topology, the unit square in R2 is closed. It's the same thing as with the unit disk, the closed unit disk. But under the risky topology in R2, it's not closed. Why is it not closed? Well, again, our closed subsets are going to be preimages of closed subsets, so they are finite unions or arbitrary intersections. That's how weak topologies work. We just take the preimages of the subsets which are closed to open to get the closed to open subsets in our domain, or set with inducing a topology on, and we declare those to be closed and open, depending what one is taking the preimages of. Notice that because the preimage of an open set is open, that's the same as saying that the preimage of a closed set is closed, because preimages of complements are complements of preimages. So for the unit square in R2 to be closed, it's the same as to say that the unit square is the preimage of a polynomial map, under polynomial map, of some finite subset, or a closed subset of K, of R. And then maybe we have to also take a union of these, a finite union. So for the union square to be closed, it's the same as to say that the union square is a finite union of preimages under polynomial maps of finite subsets of R. But if you think about it, the preimage under polynomial map from R2 to R of a finite set, well, it's just a union of what the preimage of the points. Basically, it's just a bunch of curves defined by polynomial equations. For example, the curve y squared equals z cubed, y squared equals x cubed is the preimage of 0 under xy maps to y squared minus x cubed. And these are really the only kind of things we declare enclosed, except the whole space, which I forgot to add at the top of the page. It's also the empty set is open in the cofinite topology. So really, we can only kind of get proper closed subsets which are one-dimensional in a sense. And 0, 1 squared is kind of two-dimensional, so it's not closed in R2, and it is a risky topology. So we get a very coarse topology. It's coarser than the Euclidean topology. So every subset closed under it in R2, or open under it, is also closed or open under the Euclidean topology, because all polynomial maps under the Euclidean topology are continuous, and so by assumption, the way we defined the weakest, the weak topology is the coarsest topology for which these are continuous. So any topology for which are continuous is finite. So the Euclidean topology is finite. So any subset closed under the risky topology in R2 is also closed under Euclidean topology. Notice I'm comparing the topology to Euclidean topology and the Zariski topology. We can only do this for k equals r. In general, this gives us a more general topology in any field, and this allows us to talk about continuity between maps between powers of a field. And this is actually something we can then do with algebraic geometry and talk about. But another example of a subset which is now closed is just the graph of the parabola, the graph of the quadratic map, x to x squared g on slide 2. The parabola, it's closed because it's the preimage of the singleton zero on the x minus y minus x squared. It's the same thing as I mentioned before. We know that this polynomial map is continuous by assumption, because that's the risky topology is the weak topology with respect to polynomial maps. We know the singleton zero is closed because it's a confined topology, the weakest topology, the closest topology under which singletons are closed. And so a preimage of a closed set is closed, and we get that this parabola is closed. So really, what one does with this risky topology, one, instead of picking out all of the closed subsets, one picks out the closed subsets which are cut out by polynomial equations, which are going to be lower dimensional Tajon space, except when one has the whole space, and when the class those is open. Those is closed. And this is the topology one gets, and we can talk about this topology. It's a very different topology than what it has usually. At least, again, in the case of R, otherwise it doesn't really have a usual topology. It's not housed off. Any two open sets intersect, which are non-empty. Such topology is called irreducible or hyperconnected. There are many interesting properties. And actually, while it might seem obscure at first, the properties are quite nice for what one needs them to be. Many of the properties, as one uses them, turn out to be quite helpful, and one gets a nice terminology when one uses in the general context of algebra. And one note to add, this definition of the Zariski topology is essentially the same as Oskar Zariski himself gave when he first defined these things in 1944 in this paper. But nowadays, the Zariski topology is a more general phenomenon. So in the beginning of the lecture series, we'll define this Zariski topology, then we'll move on to the more general Zariski topology. And it's more general in the sense that we define it in a over class of things, on ideals, prime ideals of a commutative ring. And it turns out that this topology on Kn is kind of a subspace of the over the topological space Kn under the Zariski topology is a subspace of the more general space one gets with the Zariski topology. So actually one generalizes modernly. So just to mention, sometimes you will see the Zariski topology mentioned while talking about the general, different but kind of more general topology than this. So that's how these topological notions play into algebraic geometry. Okay, so that will be the end of my talk. Here's some general references you can read. So some nice topology books, some of my favorites. So the Engelking book is both of the Engelking books are very nice. And also I like the Circoid purely metric space book and Kaplansky mostly metric space book. Okay, so before ending, any questions? Let's give it a second. Oh geez, I've been going for 1.5 hours. I thought this was going to be 30 minutes. Slow talker. So people are complaining about me talking too quickly for the recording. So on the recording, you can, on the YouTube video, click on the three buttons top right, and then you can like go settings and do all 5 speed if that's too quick. But actually, I don't know. I've been listening back to my recordings and I put them on double speed. I think I don't know. I can make out what I'm saying. I think so. So okay, I think I don't think there are any. Are there any kind of valid questions besides talking about how quickly or slowly I talk? Well, sure. Let's give it a minute. I mean, this recording can go on for a little longer. I mean, we've been talking about having the Algebraic Anonymous podcast is kind of like this, except you can only hear me. It's like you filter out entropy. So you figure out your question. I don't know any other questions. Mhm. Yeah, I'm happy to see that a lot of people attended after all. When we first started, almost nobody was here. We could, but I'm not really sure what the Algebraic Anonymous podcast would be talking about. I mean, usually the usual topics of discussion, I'm not sure they would quite be appropriate. FU, how's the question figuring out going along? So yes, the question is how did I apply De Morgan's law, and I didn't really apply it on a specific slide, but the general remark to keep in mind. Let's go back here. So we've seen that the preimage of an open set being open for a function with topological space is equivalent to it being continuous. Actually, we can replace open here with closed. A function is continuous between topological spaces whenever the preimage of a closed set is closed. That's equivalent. And the reason you can do this, oh, actually, I'm sure that's where I applied De Morgan's law. This is one place. Okay, this is not De Morgan's law, but it's okay. Sorry, I'll mention this as well, but it's not De Morgan's law. I'll have to. Yeah, I think I know where I applied De Morgan's law. But let me mention this as well, because it's also good to mention. So it's equivalent that the preimage of closed set is closed, or the preimage of an open set is open, because preimage taking commutes with complements. So if the preimage of a without x, preimage of y without u for u open is closed, then that's saying that the preimage of u, the complement of that is closed. So the complement of the complement of the preimage of u is open, because the complement of a closed set is open, because the closed set is a complement of an open set. So the preimage of u is open. That's not De Morgan's law. That's the fact that preimage taken commutes with complements. De Morgan's law I applied to mention that, well, we've seen that arbitrary unions of open sets are open and finite intersections of open sets are open. But by De Morgan's law, because if you take a complement of open sets, we get closed sets, arbitrary intersections of closed sets are closed, and finite unions of closed sets are closed. This just follows if you write down, you have some closed sets, A1 through AN. Well, they're closed, so the complements are open, so you can write them as the complements of open sets U1 through UN. And then you take a complement of their union, and that's going to be an intersection of the open sets, and it's going to be open, so the complement is open, so it's closed. So what De Morgan's law gives us from our definition of a topology is the fact that one can equivalently require that arbitrary intersections of closed sets are closed and finite unions of closed sets are closed. That's where I applied De Morgan's law. Okay, I hope this answers the question. Okay, so FU, you have a question about continuity? Well, okay, we can discuss it later. Any other questions before we end the talk? Yes, so the question is, would the intersection of all topologies on a set be the closest topology in the set? And this is true, it's going to be the indiscrete topology, because by definition it's the closest topology is topology containing all the topologies, and it exists, we're going to prove that, and that's the indiscrete topology, we can check that. So yes, it's true. Yes, so if you have the weak topology on a set X with respect to a family of functions from the set in topological spaces is the intersection of all the topologies for which these functions are continuous, all these topologies in X. You can generate topologies this way. And yes, this is true. You can check it this way. Okay. Any other questions? Okay. I guess no other questions. Then thank you for letting me steal 1.5 hours of your time for topology. And thank you for listening to my talk. Yes.